see?
Yes, yes.
I just switched on the video. Okay, fine. So good afternoon. I'm Ram. So today, I think in the last couple of weeks back, we had discussed about having a session on this home-built radio astronomy and radio telescopes, and that was the subject that we are planning to do today. And what I am planning to share is our experience of building and doing some astronomy out of the radio telescopes that we have built at home. When I say we, I also have Srirang, who is also joined the call. So Srirang is currently in Nagpur, but we both have built this radio telescopes together. So today I'm planning to present two radio telescopes, which I will probably show that later as well. But along with me, Srirang, and we both have built this together. And just to share a small journey, around year and a half back, we both were together studying a postgraduate course in astronomy and astrophysics. So, as part of the course, one of the subjects was radio astronomy. So, as part of the radio astronomy course, which was one of the subjects, we did visit the Gauri Bidnor radio telescope facility. So, when we visited as part of our educational tour and all that, so that's when we saw what was being done there. And then over just a casual lunch discussion in Gauri Bidnor itself, in the facility, myself and Srirang, we thought, why can't we build one where we can do some radio astronomy out of it. So that's how the journey started. Around that was sometime July August last year, and then and in the first trials that we did was after 3 months we were able to assemble and build something within 2.5 months, and then we started our first trial. And then, as part of this course, we did present a paper which is a part of our dissertation to complete this course. And the paper that we presented was on radio astronomy and how we can build radio telescopes at home and do some observations and derive some science out of it. So that's the just a prologue of what we did. And I'm sure if you have seen the camera, what you're seeing here behind me is one of the radio telescope that we have built. This is a new antenna which we have designed during the lockdown. We have designed a couple of them. This is one of the versions, and this version that we have designed is for the hydrogen line observation, which I'll also try to talk about that in the next few slides. So that is the prologue, and what I'll do now is switch off the camera and start the presentation. I have a set of slides which I feel is much easier to walk through and talk about it, and that's how I plan to conduct this small session. I hope it's okay. Yeah. So I'll just switch off and.
So one more small submission. I think this talk is going to be of some utility for some of my students also who do projects. If you permit, then can I just pass on this
Sure.
link to them?
Sure, sir, sure.
So maybe in between you'll, Parminder, you might have to like admit them, some unknown individuals.
Okay. Sure.
Can turn up. Thanks. I'll just do
You
that.
can continue. Yeah.
Please.
Sure. Okay. Yeah. Let me know when you're able to see the screen.
Okay.
Sure. Okay. Yeah. So here is the couple of pictures of the actual radio telescopes that we have.
Sorry, sir, but your screen is not visible to us.
Oh,
No,
I'm sharing.
It is
It
visible.
is visible. Okay. 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 Okay.
You just need to
Okay.
unpin his camera.
Okay. Right. 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 Okay.
It's
Thank you.
it's it's visible. Okay,
now.
fine.
Now it's okay. Now it's okay.
Okay, so I'll just walk through a set of slides now. That's where now the pictures that has been put here is the actual pictures of what we have built. And on the left side, where there is a dish antenna, that's a solar radio telescope, which is used for chromospheric observation. And then on the right
Screen
side,
largely enlarged. I'm not sure if others are experiencing that. I'm not able to see the full slide, but one portion of the slide fully maximized. Not sure why.
oh, is everybody experiencing the same, or should I probably do something?
I'll
No, I can visible.
No.
I'll just WhatsApp what I'm seeing. I'll just WhatsApp on the group what is becoming visible to me.
Okay, are you able to see the full
So
screen?
I've just
I
sent
see.
the screenshot.
I see the poster. Your full poster, in
Okay,
which
fine.
on one side there is a disk and there's something text on one side. I think it
Yeah.
is okay to me. I don't
It's
know.
okay for me.
Okay.
Oh,
Srisha,
okay.
sir, please have a look at what I've just sent on the group.
Yeah, that's the full picture. What I just
Okay.
checked the WhatsApp. That's the full picture. That's true. And there's, I think,
Okay.
maybe Srisha needs to just recheck on his
So,
video orientation. Yeah.
Shrisha, please rejoin the meeting. Then I think screen issue can resolve.
Okay.
Okay.
Can we continue? Okay.
Sure.
Sure. Okay. So yeah, on the left side, the parabolic dish is the solar radio telescope. It is based out of a IBT design. IBT stands for itty telescope. I'll talk about that once again later. And then on the right side is about the 21 centimeter hydrogen line detection. It's a radio telescope for that. And you see three telescopes there. Each one of them are actually different versions of that. It means that
नहीं नहीं
it
यार
goes
तो बोलिए मेरी मीटिंग चल रही है मोटिवेशन
it goes from down to up. It's many versions that we have been building for the last 1 year plus more, and each one of them have got its own distinct advantages in terms of gain efficiency and resolution and bandwidth and so on. So which we will also try to take a short look about it later as well. Okay, so I plan to start with giving a short introduction of what radio astronomy is all about. Now, and what's the difference between visual or optical that is normally done versus what is radio. Now, the basic difference between radio and visual are both are electromagnetic waves. Once again, it is just that in case of radio, you can look at this particular picture on the left side. Uh, it where what radio astronomy does is that it studies the emission of radio signals from celestial objects at radio frequencies, and where you have a visual spectrum, which is around 400 to 700 nanometer. Radio telescopes observe the skies in wavelengths from centimeter to a few meter. So that's the difference between the electromagnetic wave length differences between radio and visual. So visual is in a very small wavelength. This is the visible part. I'll just draw. So is where here. So this is where radio astronomy comes in. Now, from the point of view of the window of observation, I'm just shifting to the slide on the right. You can take a look over here. That this is the visible light that we can see, and this is a very narrow band. Whereas when you look at radio is a very wide band application. That means you can see you can resolve a lot many more objects in radio frequencies when you use radio telescopes than going visual. There are certain distinct advantages as well. When you compare both, most of the time optical signals are or do have a lot of bearing on how the atmosphere is, the turbulence of the atmosphere, the weather, the cloud, and all that. But a radio does not get into those kinds of interferences. It is able to much more resolve, much more wideband, plus also not getting into all those atmospheric seeing kind of challenges which optical um, uh, signals do have. So that's the main difference. But there are certain places in which even radio is not able to resolve. Those are typically infrared, gamma rays, and long wavelength radio waves, which are typically blocked by our own atmosphere. Now that's the major difference and when it comes to radio versus the visual. The only advantage, once again, I try to repeat, is that we get a much broader observable window from the Earth when compared to an optical window. Okay, so there's no hard and fast rule. If you have questions, please stop me then and there, and we can keep discussing about it. So the next, I'm trying to go much more, a bit more deeper into what radio astronomy and how it really helps us. Now, once again, this slide is about the comparison between the optical and the radio windows. Now, when we can see it is a very broadband radio window here. And what this picture talks about is how atmosphere most of the time does have a bearing on what we observe in the optical window, and how the atmosphere does not have too much of bearing when we observe something in the radio window. So when we start talking about the atmosphere, various layers of the atmosphere, right from troposphere, stratosphere, thermosphere, and mesospheres, and each one of them have a certain level of absorption and kind of when light does come through the atmosphere, it does affect the atmosphere, does affect the way that we see the or visualize certain objects. That's why many of these telescopes like Hubble are placed up in the sky where it is free from all the atmospheric turbulence of the Earth, and it does have a very clear view of the celestial plane. So that's where many of the telescopes like Hubble and all are placed. And since infrared is blocked by the atmosphere, there are specific satellites which are placed which do capture celestial objects in the infrared spectrum. And then there is X-ray, Chandra X-ray telescopes, and then there are gamma waves which can also be detected using certain satellites. Now, for the radio window, especially since it's got a very broad spectrum, many of the observations or most of the observations are Earth-centric. So they do mostly from the Earth itself, and that's what something which is interesting. Um, so this is just at the end of the slide. I've just kept a small idea of how we can compare the lambda, and that is the wavelength of a particular radio frequency, and convert that into frequency, and what's the formula for that. So lambda is the wavelength, c divided by f gives us the wavelength, c is the speed of light, and f is the frequency. You can always do conversion. So most of the time, if somebody tells you that we have to observe a window of 21 centimeter, then you'll have to find out what is the frequency that we'll have to build an antenna or design an antenna for. And then you can use all these formulas to do all that conversions and find out those basics. So I just left it like that for that. Now, yeah, I'm just going into detail about what we can do as some projects, as most of us are mature astronomers here, what we can do as some radio astronomy projects using SDR. We'll talk about SDR also. SDR is called as a software-defined radio. So it's just a small electronic gadget where it has got all those amplifiers, low noise amplifiers, sometimes filters, and then it comes with a complete package of even coding, decoding, encoding, and all that in one single small device. So that's SDR. So you can do various projects of radio astronomy using that device. I will also show the device later. And these are a few examples of what can be done as radio astronomy projects, which you can do yourself at home and so on. So I'm just trying to give a brief introduction of what all can be done. So ionospheric monitoring can be done, and this is at ultra low frequency and very low frequency, and mostly at around 30 to around 3 to 30 and megahertz and kilohertz and hertz. And Jovian is typically the Jupiter. So Jupiter also emits radio signals because of its very high dense magnetic fields concentrated near its poles. And Jupiter has got its own rotational pattern where we know that it does a cross rotation and of its gaseous medium. And because of that, it does produce a lot of radio signals, and those can be detected using antennas from here on Earth, and that is detected using at around 150 to 250 kilohertz. So this is something which is also done by hobby enthusiasts. And then you can do a lot of solar observation, uh, typically solar continuum, solar wind observations at very high frequency. And then many of the observatories, even in India, like Gauri Bidnor, they observe solar at around 70 to 135 kilohertz. That's their observational window. And they have built a large aperture telescope there. If somebody has seen it, even on the web, you can see it's a 2 kilometer long telescope, which has got a lot of Yagi antenna array. And they observe sun and map the sun using radio medium. And then you do have pulsar observations that you can do, and typically it is from 70 to 406 kilohertz, and you can design your own antenna and do a pulsar observation. So and typically one basic thing is that so long the wavelengths become the frequencies are lower and lower, the wavelengths are broader and broader, the antennas have to be much larger in size, and and when the wavelengths become shorter and shorter, that is, in frequencies become higher, the antenna can be smaller. So the portability does come when you have a certain something which is at very high frequency. So that's why most of our cellular phones does have that portability, because they operate at around microwave wavelengths. Yeah, that's some basic. And then yeah, we can also do a lot of solar observations. I will come to that part as well. Sun is a great radio source. It emits radio, multiple bands of radio frequency bands, and that's something where you can observe sun in its many dimensions using radio frequency. We'll come to that later. That's one part that we can discuss. And of course, this is the 21 centimeter hydrogen line. That is something that can be observed. Plus, the sun also emits something at 1420, that is 1.42 gigahertz, which is solar continuum. Continuum is typically a continuous signal which will come from sun, and this can be observed and captured as well through radio frequencies. Spectral is typically the hydroxyl radical. This is used in mostly astrobiological applications now, also in SETI. SETI stands for Society for Extraterrestrial Research, and they also find out if there are any other living sources other than us somewhere in the universe lurking around, and they use these methods to find that out. OH typically, because there is an oxygen and hydrogen kind of a combination. Always, if you find something here, the idea is, or the hope is that you can find somewhere a life other than us somewhere in the universe. So that is also used in radio frequency observations at 1.6 gigahertz and 1.7 gigahertz. So these are a few projects that can be done. I have have stopped it around 1.7, but there are many others as well. But many of the commercially available SDRs operate better at only up till 2 gigahertz. And after that, you will have to have some special SDRs, which are typically radio astronomy SDRs, which are not that easy to procure in the market. But there are many other projects that can be done.
Ram, Srisha here, a question. Am I audible?
Yes. Sure, Srisha. Yes, you got it.
Yeah. So these radio telescopes, they are limited for visual observation, or they used for imaging?
No imaging comes out of this, Srisha. No imaging
Okay.
comes out of this. This is purely where I can show. I'll show you. Actually, I have few videos. What you really get as signals. So you will be able to see signals. That means waveforms which form or pulses that come out. Typically, once you are able to resolve a target, and from there you capture all that data, and then you can do a lot of analysis from where the source is, what is the what is the source made of, and so on and so on. So I'll show you, but there's nothing. Optical is nothing that you can do with your radio.
Okay. Okay. So more for research purpose and understanding specifics of the target.
Yes.
Okay. Thank you.
And also what radio does, what visual cannot do, is that it can go much far or farther than optical.
Right. Yeah. Got that. Yeah. Thank you.
Yeah, so that's a distinct advantage, and you can do a lot more science with this than optical. Optical does give you all that visual depth and clarity and pretty pictures and so on. But here, a lot more science can be done. We'll talk about that some in the next couple of slides of how it is really useful.
Sure. Yeah.
Okay. Yeah. So now coming to what we have done. What Srirang and myself we have done is we have built two radio telescopes. One is for observing the sun's chromosphere, and that's at around the emission is at around 10 to 12 gigahertz from the sun, and we are observing that here through our own IBT-based design, and then hydrogen line telescope. Hydrogen line is emitted from a lot of galactic sources, supernova remnants, and so on. We'll also get to know why it is so important in the next few slides. And that is what we have built. These two telescopes is what we have built. In the new design that we have done, we do have it's an optimistic or a design where we are planning to also use this in both spectral 21 centimeter hydrogen line, also to try to do something with the OH hydroxyl radical kind of observation. But this is still yet to be tested. We have just designed this, and the hardware is all ready. Right now, we are doing a design of experiment to actually put this together and start resolving and getting information. Yeah. So I'll go a bit more detail into what we have done. The first introduction is about the chromosphere radio telescope, which we have built for observation of the sun's emission from the chromosphere. And this slide talks about what does sun radiate, and what is sun a radio source. So, and how it is a radio source, and why it is so important to observe the sun in radio frequency. So sun is a great radio source, and what it does is that it emits in a very broad band in terms of radio, right from 20 megahertz to 20 gigahertz. It can be observed, which is a very large band. Apart from whatever we visually see using H alpha or any of those visual observations of this. Sometimes we also see all those coronal mass ejections and photospheric dispersions and so on. And prominences, of course, using all that visual telescopes. But radio is also a very important observation that people have been using for observing sun because of because of the broad amount of frequency that is emitted from the sun. So if you look at the picture there, so each layer of the sun emits a radio frequency. The photosphere does emit, plus there is also emission coming out of chromosphere. Then there is a continuum, solar continuum coming, which is typically the radio sun, which is every day sun as it starts shining because of its thermonuclear reactions, and there is a continuum which does come, and this is also observed here and mapped. And if you look at this graph on the right side, I'm trying to point it towards a small rectangle within the graph. So this gives an idea about the frequency, say from 10 megahertz to almost 30 gigahertz. So you have various kinds of emissions which are coming. So wherever there is this cross lines, they are all called as solar continuum, which means it's a continuous emission coming from the sun, and each one of those continuum is coming in from different layers of the sun. So there is decametric continuum, then there is decimetric continuum, and so on. And then there is this microwave continuum. This is where we have done something about, and this is coming in from the chromospheric part. And there is also this decimetric continuum, which is also coming in from the sun, and this is also resolved through the new radio telescope that we have built. And I think about couple of weeks back, I just put a graph about what we have resolved. So that resolution was sun's emission coming from this part of the decimetric continuum. And that's how you can observe through radio. And how do you start capturing, and what you can do is in the next few slides I can explain. But what this graph shows is that as and when there is a lot of variation which is happening on the sun, wherever there are sunspots which is either at the maximum or minimum, when there is a quiet sun, or it's a normal sun, or there is a noise, or there is a burst, all this can be found out through radio. And that's how it's very, very important that people do observe the sun. And because there might be so much of coronal mass ejections sometimes, which it does happen, and many of the satellites which are orbiting the Earth, and they are all made up of electronics. A ton of electronics do work on Earth, and if there are coronal mass ejections which are of very high intensity, there might always be a burnout. That means that all these electronics chips or electronics, they just stop working. And there have been these kind of instances which have happened earlier, and they do observe sun for those reasons. Not visual, yes, but radio is more to observe those kinds of rejections. Okay, I'm just going into the next slide, where this slide talks about more of our own design and what we have done. So what we have done in our case is we have just taken a dish antenna. This is a normal parabolic dish antenna which is used for all our cable TV receptions. So I had a spare one which was used for earlier dish TV or something. So we just modified that for observation of the sun. Now, the reason that we used this kind of cable TV dish antennas is that we would have seen an LNB in front of the dish antenna, that small block which is typically there. It's a waveguide called as low noise block. What that does is that whenever the dish antenna is pointed towards the source, in this case, when we are trying to look at all these satellite TV channels, if you point it towards the satellite where it's Earth-centric, that means that it's always at the same, somewhat at the same point. So it starts beaming there, and they use L-band. L-band is typically what they use, and here the L-band, these kinds of LNBs work from around 10 to 12 gigahertz. That's where our satellite TV reception comes in. So you can use those LNBs, which is normally used for satellite TV reception, and do some modification to start getting signals from the sun for this. So that's exactly
Excuse me, sir.
what we are trying to do.
Can you please hide the notification at the bottom regarding presentation?
Oh,
It's
sorry.
obstructing the view. Yes, please.
Okay. Okay, is this okay?
Yes.
Okay. So we use an LNB. The low
Sorry,
noise.
Ram.
Yeah.
Uh, can you explain about what are the modification you have done this LNB?
Yeah, I'll come to that. I'm
Okay.
just getting. Now, the LNB as such does not require any modification. The LNB, whatever you are having in a satellite TV reception, you can continue to use that. So the only change that we have done is that uh, normally what you have at home is a single port LNB, unless you have two connections where it's using a single satellite dish, but you have two connections at home. Otherwise, most of the times you get a single port LNB. Instead of that, we ordered a dual port LNB. So it's not that expensive. You do get it in Amazon and all these places. It's around 500 to 600 rupees. So you use that, you get a dual port LNB, and then what needs to be done is that you take that and you have a something called as a satellite TV signal receiver. It's a small red color box. I'll show you that. I do have a picture. So what it does is that many of the people who come and install these dish antennas at home, they use this to measure and find out where the signal is coming from, which direction, and then they bolt it and go. So it's a small device which works on an 18-volt battery and so on. So what it does is that as soon as you turn the dish antenna in the direction of that satellite, it just gives you there's a meter there. So it just the needle starts pointing towards the higher band, and it gives out a buzz or a beep. So that is what is used. And then even this is available. This is very inexpensive. It's around 200 to 250 rupees. And you use a normal coaxial cable, which comes whatever is used for your dish antenna. The same coaxial cable can be used, and one of the ends of the coaxial cable needs to go to these these satellite TV reception meters, and then from the other port, this is connected to from a coaxial cable RG6 to RG174. There is a conversion that I have done. So that means you just cut the coaxial cable which comes with the cable TV, and then you have to give it to a slimmer one. I will show that later. And then this can go into your RTL SDR receiver, and then this will plug in via a USB socket to your laptop, and then you can use some software called as SDR Sharp or a radio SDR and so on, and then you can start receiving the signals from the sun when you start pointing the antenna to the place where the sun is there in the sky. That's how simple it is in terms of actually building the whole stuff.
So Ram,
Once,
I have a question.
yeah.
So the input in the RTL SDR wideband LNA so
Mhm.
comes from this 18 volt. This device RG6 coaxial cable wire, or from where?
Oh,
Input
okay.
from this in this box.
Okay, so now I'll just talk about that. Now the 18 volts which has been put there is if you look at what we have at home, all our cable TV receivers, there is that box, right, which is got which actually one of the end of the box connects to the TV, and it has got a coder decoder box, isn't it? You've seen those, right? Small ones which is plugged in near the TV, and then you use a remote to switch the channels, and it comes with a set-top box, correct?
Okay, okay.
Now the set-top box, what it does is that the one end of the set-top box is connected to the coaxial cable, right? So the set-top box, it provides around 18 volts as a back voltage for the LNB to operate. This LNB, yeah, to operate.
Okay.
What we are trying to do over here is artificially providing this. You can use an 18-volt power supply, a DC power supply, and then a small inductor to isolate it, and directly feed it through this satellite meter, and this LNB gets powered through that, and then this is able to receive all the signals. Okay. I'll show you. I have a video. Yeah, I'll show you. So that's the mode of operation, and then you can use a set of software to start reading the signals. This is how it reads when you open the software, and this is at around 1.2 gigahertz. So what this does is that this LNB, it takes the signal coming in, incoming signal at around 10 to 12 gigahertz, and down converts it to 1 to 1.2 gigahertz. So, and then this down converted signal is what is going into all these wideband LNA. Wideband LNA stands for low noise amplifier. It's just an amplifier to amplify the signal which is coming in from the LNB, and then we are feeding it to the RTL SDR receiver. It just gives a bump in the signal and gives some amount of stability, and you can do a lot more analysis when you open up all these field Fourier transform softwares like RTL, like this SDR, and then radio SDR and various other softwares which typically do all that. And this is where we are trying to do at 1.2 gigahertz this observation. You are able to see a spike here, a peak. You're able to see this peak here, right? So this is the signal coming in from the sun. If I switch off this 18 volt, this whole signal will die down, and it will be a flat noise here. As soon as I switch on, and if this whole antenna is pointed towards the sun, I will get this spike. So this is how the signal from a celestial source is received, and then you can have all these meters and plugins and so on, which will show you what is the strength of the signal, and then you can store all these data and do a lot of analysis. I'll come to that part later. Yeah, this talks about what are the dimensions of the dish that we have used, and we just used a counterweight to balance, 2 kg counterweight. This is the actual picture. The red and yellow part is the LNB, which is there are 2 ports here, and then one of the port. This is the satellite radio. It is just a signal receiver. It's a small box. This is the box, and then one port is connected to this, where it detects the signal, and the other port via the RJ, the coaxial cable, and then it is connected to the laptop. So this is the basic setup of the radio telescope. Just put this on a normal tripod, which is used for most of our camera. A bit sturdy one, because this whole thing weighs around 3.5 kgs, and put 2 kilo of a counterweight. This is a normal counterweight which is used for as an ankle weight in most of the exercise that you do in gyms. So that's what I used here.
But it is a tracking device.
No, okay, this particular thing is not a tracking device. I'll show you the other one which we have built for 21 centimeter. That I have mounted it on the Ioptron Skyguider Pro. It's a very lightweight equipment that we have built as an antenna that keeps tracking. That is used as a tracking device. That can be used as a tracking. This is not tracking.
Ram, do you have output of how these scopes show us?
Yes, I have. Okay. I'll show you a video. I'll show a video now. Okay. So I'll just show a video now. Now there's on the left hand side, if you see, there's a picture here. of the dish antenna, and there is a set of mirrors that I have placed on the dish antenna, right? And then the sun's reflection falls on the mirror, and then it's getting illuminated on the LNB part here, the yellow color part here. You can see this. So this is very important to find out, because many of the parabolic dishes that you get either are center focused or offset focused. So what we had tried to do was that this particular dish was an offset focus. Now we wanted to find out what is the degree of offset it is, so that when we point it towards the sun, it means that it's just like, you see the sun, and if this telescope is in alignment, it will not work because it's in offset. So there will be a 10 or 15 degrees difference. So that is what we wanted to assess before we actually do the experiment. And in order to do that assessment, we just use some mirrors and a small set of piece of mirrors which you get in any of those mirror shops, and put some magnets around it with a sticky tape and place it on the dish to find out the offset. And then we'll have to also do some final focus adjustments here, just to ensure that the right amount of sun's energy falls on this, and it's in all good focus, that we can get a high intensity output. So these are a few things that you'll have to do once you build them. Okay, now what I'll do is that I'll just switch on the video. Um,
Just a small suggestion, can we also paste small specks of aluminium foil on the dish itself rather than mirrors?
yeah, you can use your own method. You can use your own methods. That is fine.
Okay, thanks.
In fact, aluminum is very good reflector of radio waves, so that would be very helpful. Yeah, you can use radio. You can use aluminium as well here, because we are able to visually see the sun much better, and most of the time, it so happens that if you have high reflectivity like a mirror, you can visually also see the kind of beam which is forming on the LNB.
Yes, that serves as a decent indicator.
Yeah.
Aluminium
And
actually
many of
reflects
the
in
times when
all
you're in
regions
bright
of
sun, to
spectrum.
make out the difference, it is useful. That's all.
Right, right.
Okay, I'm just switching on the video. Do let me know if you're able to hear the audio as well. Are you able to hear the audio?
No.
Oh, 1 second. I will try to beam it to my speaker. Let me know if you're able to see. And this is the satellite dB meter. You can see the needle has pointed more towards the right. That means it is receiving the signal. And then these are the LNA and the SDR. And this is how the output looks on the screen. Um, and what I was trying to point over here is what's the relative temperature that when we were taking this observation. So that is why I was just pointing towards the thermometer there. Okay. And I'll try to show the next video. So let me know if you're able to see or hear this noise as well. What this does is that you can look at the needle here. It's moved towards the right. That means it is towards the sun. It is moved towards the right. Now, as soon as I physically try to move the telescope towards right and the left, where it is going away from the sun, the needle tilts towards the zero, and then it starts coming. As I move towards the sun, it becomes it comes towards the right. So it means that's how the signal is getting received. You can see that, right, when you physically move the telescope, which is either towards or away from the sun, there is also a difference in the signal. Yeah, that's all. So this is how a basic operation of the radio telescope. Um, any questions on this?
Ram, they use these similar radio telescope setups for capturing recently this black hole, right? Black hole imaging, and they presented that last year. So,
Correct.
but you said these radio telescopes cannot do any capture of image. Are those telescopes different from this one? What you showed? They are also,
Okay.
is what I read.
Yes, I'll try to explain that. So what they are doing there is adding false color. Okay.
Okay.
So it means that what you are trying to get over here, assume that you are getting 1 pixel. Okay, this is 1 pixel, one information. Here you're getting 1 pixel. Assume you are putting an array where you can get a pixel of say 1024 by 768. That means that you need to have a lot many such telescopes working in coordination, and each one of them will receive a signal, and then they integrate that signal in a typical bit, 8-bit or a 16-bit, and then convert it into a three-dimensional pattern or a two-dimensional pattern. Okay.
Okay, okay. So basically, it is not a direct capture of image, but the signals are interpreted by some softwares and they then convert it into an image.
Exactly, those numbers get represented in colors. The same way as most of our CMOS CCDs work.
Yes,
Where
yes, inside, yes.
the same way here,
I
here
guess
that is,
Because one of the things which I keep thinking, right, especially, for cities like Bangalore, where it is most times cloudy, whether a radio telescope imaging system can be done, where, we can actually image even if there are clouds, and, the signals can be converted into pixel images, and then we can actually start imaging it. And I keep thinking about that is practical feasibility.
yes, it is practical. It is just that what needs to be assessed is what is the celestial object that you are trying to resolve, number one. Trying to resolve much smaller and smaller distances, you will require higher and higher power. So you need to also calculate the aperture in terms of power to resolve, and also the power in terms of power itself. What is the kind of electricity which is required, and the amplification which is required to do all that.
I think so.
Okay.
What Srisha is willing to do is that can be achieved through raster scan of a patch in the sky.
Yeah.
Okay.
So that will give a plot of the strength of signal. That way we can make out something for the visual. I think that is
Yes.
possible, and that is what's done by the professional radio telescopes.
Yeah, I'm just trying to show, and I've just gone to the next slide, which partly answers that question as well. Now, if you look at this slide, on the top left, there is a frequency spectrogram, right? No, what the spectrogram does is that using the same setup that you have done, which was done there, we run spectrograms. Spectrograms are nothing but you take a bandwidth, say we were resolving a signal at 1.2 gigahertz. So what I want to do is that I want to find out at 1.15 to 1.25, which also includes 1.2 gigahertz, what is the strength of signals that I'm receiving in each one of these bandwidths. Okay. I run a spectrogram where it will run a series of scans. So it might run around 12, 15, 20, 100, whatever the length that you want to, or the frequency and what you want to. And this spectrogram tells you that when I run it around 15 times, 20 times, where is the maximum I'm getting? You're seeing all those blue things here, right? And then there is a peak which is marked by a red cross there, and it shows 1.2. So this is in megahertz. When you convert that into gigahertz, it is 1.2 gigahertz. And every time when I run, the peak I'm getting is at around 1.2 gigahertz. So what what this assesses is that the signal strength that I'm getting at maximum when I pointed to a particular region in the sky and resolving a particular celestial object on a date, time, latitude, longitude, all that you can you can record. This is where I'm getting the maximum signal strength, and that is where one is what you visually saw in the software which was down below in the screens which are here in the black backgrounds where you see those spikes. But these are spectrograms where you run those scans by energizing the antennas, and then you get a response out of it, and then you can start doing a lot of analysis through this as well. This is not nothing but what Professor Srini Saab was telling, that you can run a scan. So this is exactly the scan.
Yeah, got that. Thanks, Ram.
Sure. Okay. Now, once you resolve, what we try to do is that we cannot always depend on only one software saying that, okay, it has given us some result. We'll have to take different opinions of different softwares to mathematically also assess that, okay, what we are getting is actually from the same celestial object and not a noise. So that's where we try to take from various methods of gathering data. And then if they are all able to give you the same result, saying that at around 1.2 you are getting a peak, then you can trust. It's just that, you don't trust the software just because only that software is giving you data. That's how we are trying to do. And this is how we wanted to assess ourselves that our signal was right. So this was one method. Okay, so now I think that was the introduction about the solar radio telescope that we had done. So if you have any other doubts, please ask me. I'm trying to go into the next one, which is talking about the hydrogen line detection. Is there any questions on the solar part? Okay. So now I'll try to go into the hydrogen line telescope that we have built, detection telescope that we have built. Before I go into that, just trying to give a small introduction about why is it so important about this hydrogen line detection and what is the physics behind this whole thing. So hydrogen line detection is about detecting the neutral hydrogen. Neutral hydrogen is a form of hydrogen where it was formed during the dark ages and the transient from dark ages to epoch of reionization in a theory of Big Bang, where there was a Big Bang, and then for a while, I'll just go to the next picture, which is much more clearer. For a while, there was nothing, and then the matter started coming together. That is where the hydrogen, which is the most abundant element, started getting into the ionization phase, where it can start getting itself binded into molecules, then getting into helium and so on. And that actually started the star formation, galaxy formation, and the whole rut of the universal Big Bang part plus the reionization part. Now, here is where the hydrogen line detection becomes very, very important because this neutral hydrogen is part of those primordial matter of in interstellar medium. I'm sure Professor Parminder Singh Saab can explain much more, he being a cosmologist. But if I'm going wrong, please do correct me, sir, somewhere. But that's the that's where it becomes very important to detect this. This forms the primordial part of the universe, Big Bang creation itself. And then when you are detecting something like this, it means that you are going far, far, far back in time, and that's why it is so important. They are doing a lot of research on this because it gives you so much back in time. And also this particular telescope is also described as a weighing scale for the universe. because once you detect hydrogen, hydrogen is the most abundant element, and out of the total universal mass, I think 5% is only the baryonic matter, which is the matter which we can all see where stars are made out of, we are all made out of. Rest of it is dark energy, dark matter, and so on. So the 95% is a lot of unknowns out there. But this 5% of what is known is where a lot is derived out of H1 or the hydrogen line physics. So now, what many of us in astrophotography is instead are interested most of the time is also in the visible part, uh, where we look at the hydrogen alpha that is visible, but H1, which is neutral hydrogen, which is an atom which is made out of only one electron and one proton, which is as much dependent, as much abundant as any other, is not detected using any of the visual means, but it can be detected using the radio means. So what happens is actually, if you look at this diagram where there's a blue sphere and a red sphere there, the blue sphere being the proton, and where the red sphere is the electron which is moving around the proton. And there is sometimes what happens is there is spin flip which happens where you're seeing both arrows are pointed here in the upper direction. When a spin flip happens, there is a flip of the electron where the arrow gets pointed towards the downward direction. That happens because of various things. Let me not get into that part. So once it happens, this is uh, this particular instance, a photon is released, and that is what is released in form of an energy, and that is what is released at 1.420 gigahertz. That is what is called as the hyperfine line of hydrogen, and that can be detected here from Earth, and that is what we are interested in, and that is what this radio telescope is all about. Okay.
Hyper fine line,
Mhm.
photons released in that manner, do they have any specific color?
No color. This is not detectable by optical.
Okay, but if we were to convert that to an image or something using some software, would that show any color for us?
Uh, Actually, no. That's because neutral hydrogen does not have, rather, I don't know, you can add some false color maybe, but it is not, optically, this is not detectable.
Okay,
So actually,
okay,
it is in radio signal. It is a radio signal.
It is only a radio signal. The energy which is released at that point of time can be detected only through a radio means, and that is not converted into we saw in the first slides. The optical is at a much kind of lower frequency bandwidth, or the wavelength is much shorter. Yeah.
But I think that one can do false coloring for that.
Yeah, false coloring is possible. Once you get through radio, you can do a false coloring. Yeah.
okay, okay.
But yeah, that's the. Now, I'm just trying to go once again, just to get into a bit of details about why it is so important. Now, this picture on the left is about the whole nature timeline itself, starting from the Big Bang down at the bottom in the Dark Ages, and then where the vertebrates and earliest apes are formed in much more recent history from the universal timeline point of view. But what we are interested here is after the dark ages, there is where the earliest stars and earliest galaxies and so on were formed, and here is where the epoch of reionization happened. So a lot of matter which was in the dark ages started clumping together. Um, why is still a question which is answered, yet to be answered in much more detail, I feel. Is it true, Parminder Singh? So in the why it happened is still a question which is yet to be answered. But we know that it happened, and that is where is the epoch of reionization was. And here is where most of the hydrogen line physics is dwelling on, or that's where we detect most of these lines from. That means whatever you detect using this telescope, you are touching something which is so primordial. That's the that's the kick, or the thrill that somebody gets when you actually detect something out of it. Okay. Yeah. So, Parminder Singh, sir, you want to add something about from the hydrogen line part from the cosmological point of view? I think, yeah, it would be good.
I think he's got some connectivity issue. But this has been a very
Okay, right.
interesting discussion. Yeah. So
Fine. So yeah, I'll go to the next slide then.
please,
Yeah.
yes.
Sorry, Ram, one more question.
Sure, sure, Sriksha.
I just want to go back to the topic of the electron spin, which you mentioned there, which you mentioned that it might have many reasons why the spin happens. But here, you also mentioned that the photons are emitted because of the spin, right?
Yeah,
Particularly.
yeah,
But in normal circumstances, the photon generally gets generated when the electron jumps from one band to the lower band. Is that the
correct,
same? But this is different here.
correct. It's the same. If you see this diagram, I'll just flip back to the previous slide. You can see the hydrogen energy levels diagram here. Yeah.
Yeah.
So this is a visible part. You see that the electron is jumping to the lower energy levels. This is the hyperfine line where n is equal to 1. Okay. The visible is at n
Yeah,
is equal to mostly 5.
but there in the visible spectrum, we do not mention anything of the electron spin, right? It's more of a jump from one band to the other band.
Yeah,
Or
it is because of already it is in the excited stage. We are talking about neutral hydrogen, and that is not a neutral hydrogen that most of the beta.
okay. Okay. So in case of a neutral hydrogen, it is the spin that actually emits the photon.
Correct. The spin flip that emits. That spin flip is because of quantum physics and quantum mechanics.
Okay. Thanks.
Okay, fine. So next, I'll just go to the next slide now. Now that was the basic background of why this whole thing is so important, and that's why it makes it also important to build something and do some trials yourself. And that was the whole idea that I worked along with Srirang, who's also there on the call, to build this. So we started building something which is very nascent, naive, and in the early days, where we just used a small dipole antenna, where we converted the 21 centimeter into when you convert that frequency, it's around 1.4 gigahertz, and then the wavelength is 21 centimeter. So we went with the half dipole design, and then we started building a dipole with a reflector and started playing around with a lot of design to arrive at the best antenna. There are many ways to isolate and detect this hydrogen line. Our idea was to build something which is portable, because typically the observatory scale, or even where some university students who do all these kinds of projects, they use horn antennas and they use dish antennas and so on. Now the horn antenna, when you try to build them, each one of them is around 4.5 to 5 feet, which is massive. And then and the dish antennas are also 1 meter to 3 meter to 5 meter to 20 meter. They're all very massive structures. Now when you have to use them and at home, and then you'll have to do some physics coming out of it. uh, One is the budget constraint, next is the power, next is the time, what we have with us. And what we wanted to do is something portable, where you can lug it, carry it around, and place it on wherever you want, and mostly which you can carry it in a shopping bag, a normal shopping bag which you can carry it around, and which is lightweight. That was a few parameters that we had in mind, and that's when we started experimenting on building with those fundamental parameters, and that's how we have been trying to improve. So with that philosophy. Okay. So what we have tried to do, I'll just show. This is a dipole with a reflector behind, and then you use a coaxial cable, and it goes through. instead of a normal wideband LNA, we are using a hydrogen line filter, a sawtooth filter, which is used specifically for hydrogen line detection um, uh, and analysis. This is a sawtooth filter which is available from Nuelec company, and that is what we have used, and then paired it up with an RTL SDR. And then rest of the software and so on is the same. It is just that the antenna design here is the most crucial thing, and plus the usage of the filter. I'll just show. I've just gone to the next slide, where you can call it as the Mark 1 of our design. This was the Mark 1 of the design which we did, and we did some analysis on what is the signal strength and characteristics of the antenna that we have built. This was built using a kind of a dipole. This dipole is to look and see is something. If you have seen old black and white TV sets, and you would have got an antenna with it, it looks very similar. And what we have used as a reflector here is a cake tin, what is generally used for baking. So that's a tin which we used, which is made out of aluminium, and that we used as a reflector. And this is the conducting elements. Those were the first designs that we did. We were able to detect something, but the resolution and the strength were not that good. And from then on, we have been making various trials to make it better and better. And still the trials are on. And something which we built a month back is what I just showed when we started this lecture.
Okay, may I ask a question?
Sure, sir.
For the reflector, do we keep a gap of lambda by 4? That 50 mm which you have mentioned.
Yeah. So everything depends upon the design. So
Mhm.
now whether you want to keep it gain that you want to have and all that parameters. I'll come to that once again later. I have a small topic on what we need to do to make the design better.
Okay, okay. Please carry on.
Sure. Yeah, this is just a picture which shows our journey of what we have done. Um, the picture down below, where there's a rectangular plate, which is once again a baking tray, and we hooked up a small dipole there, and that was our first design. And then we put up another, once again using a reflector, which is a baking tray, but this time we used this is a biquad. We built a biquad antenna. This is a completely different kind of a design, using a biquad. This had got its own distinct advantages. This was good as well. And then during the early days of May, we built a new design, which is a strip parabola design with a Cassegrain kind of a feed in front, and once again a biquad feed. So now if you look at the picture top on the top left corner, this is the whole setup. You just place a computer. So I just kept some plastic chair and a stool just to get to the eye level, and then hooked it onto a normal tripod. Uh, this is very light. This whole thing does not weigh more than 120 grams or something, and it goes easily in a bag, a shopping bag. And on the extreme right, just behind those flowery background, is our new design that we have built. This once again carrying forward the strip parabola element, but we have built a completely different reflector and director with a Cassegrain feed, which is 45 degrees off axis with the base reflector, and it still uses this as an antenna. It still uses the um, a bow tie antenna here. So all this is made out of normal aluminium sheets. Actually, what I did to build them was use most of these baking cans, flatten them, cut them, and place it in front in a shape of the parabola. and then put them together. But for us to design this whole thing, it has taken a lot of time and effort to get to the right, we can say, the characteristics right from S11 to VSWR to finding out the right gain, to finding out what is the right beam width which we require, and so on. It took a lot of permutation combination for us to get to this. So that's some of the journey that we have done. And the newest one, which is on the right side with the flowery background, is, if you can see on the red color, is nothing but the Ioptron Skyguider Pro. This is on a tracking mount. This whole thing is less than around, it's around 620 grams. So it can easily sit on a Skyguider Pro kind of a mount, and it can keep tracking the object. I can shut off the mount and make the celestial object flow through the antenna. And we can do a various combinations with this, and that was the whole idea for us to build this. So that's the whole background of how we have built that. Now I'll try to show a video once again to show how this works. The audio I don't think is required. Now, what is there on the screen over here, when I switch on the video, you can see it's already tuned to 1.420.405. That's where most of the hydrogen line gets detected at that frequency. And I will just start the video. Now, if you see the video, there is a waterfall here, which is in between. So you see the waterfall starts getting horizontal lines. So that means the waterfall is getting disturbed. And then down below, you start getting some pulses there. You're seeing those pulses. So those are the pulses which we are getting when we move the antenna across the sky. I'll just show you in the same video. When you move the antenna across the sky, there is a variation in the amplitude of the signal, and you see the antenna is getting moved across the sky. And this was the place where we were moving, where typically the Milky Way is seen. Yeah? So, and when you move it across the sky, you should be able to get those information or pulses coming in from the Milky Way, and that is what we are trying to detect in this radio telescope. So that's the basic operation, and if you have questions on this, I can take it. I'll show what we do out of this in the next few slides. Okay, slide talks about once you get a signal. This was the software which is used to get a signal. You can see there is a Keep the pointer on. Okay, you can see from the baseline there is a peak which is getting jotted out, and then it also gives you on the dB meter what is the signal strength and so on. And then if you look at here, there's a yellow portion which denotes the peak signal and the signal bandwidth itself, and then the blue portion is the kind of the waterfall, which is kind of got disturbed because the amplitude is varying. And down below you can see this is how it normally looks when you're away from the object, and when you start pointing towards the sky where there is a celestial object which has got a neutral hydrogen, which is typically here the galactic Milky Way's galactic arms, and you start getting those pulses there. Now what you do is that you do have record option of taking information, all that is seen over here in the mathematical ASCII dump, and this is how it looks. It's just a simple ASCII file, and then you store this, and then you do a lot of analysis and out of this, and that's what we are trying to do. There are a few things that you can do out of this. One is we want to find out the rate at which the arms of the Milky Way are moving, redshift and blue shift, and so on. We can actually find out at what rate that we are expanding. And then we can do a few other things which we are planning to do. I'll just stop here for a while. Srirang, you want to explain?
Yeah, sure.
Yeah, Fine. So from this data, we can analyze various things. That is like, for example, the first thing is like, what is the velocity with which the cloud that we are observing is moving. So once we are pointing this telescope towards the source would be the hydrogen cloud, which would be present in the Milky Way band. So once we are observing that, that must also be moving with respect to us. So there are a lot of other calculations that we need to do. First of all, we can calculate the shift, whether it is moving away from us or coming towards us. So that will give you the red shift or blue shift. From that, we can calculate its velocity. But after that, there are certain calculations based on the geometry. So once we do that, we exactly get the velocity with which it is moving. So that is one part that we can do. Then once we have the velocity at different locations, then we can try to plot a graph, which is also known as a rotational curve, which will give you the mass of the galaxy. So right now we are at 8 kiloparsec from the center of our galaxy. So it will give you the mass of the galaxy under 8 kiloparsec. So the mass that we are going to calculate from that graph would be the mass inside 8 kiloparsec. So this story was very much important for this plot was very much important when we got to know about dark matter. So this was the experiment which told us that our galaxy or other galaxies that are present contains certain amount of matter which is not normal, which is having some different characteristics. So this was the experiment, the first experiment to tell the presence of dark matter. Still, there are lots of other researches going on this. I think,
Shazam, actually, I have a question.
yeah.
Uh, is your device is applicable for other galaxies too, or
Um,
or or it can only measure the rotational curve of our galaxy, the Milky Way?
okay. So right now, for our telescope, the beam width is very much low. So with this, the resolving power of our telescope is also very low. So as per now, it can only detect the mass of our galaxy. But once we improve that, then we can also target some other galaxy.
Okay, okay, but this is the general application of this device.
Yeah, correct.
Okay.
So the rotational curve, what happens in the rotational curve? Rotational curve is the plot of velocity with the distance. And here the distance is the distance from the center of our galaxy. So as we move away from the center, what happens is in the general form, if we look at the Kepler's equation, the velocity should be reduced. But this is not happening once we study the rotational curve. The velocity is getting constant. So this difference between the velocity told us that there is somewhat relation between the mass and the velocity. So the cloud which are at the exterior part of our galaxy are being held up with a force that is pulling it towards inside. So that force needs to relate with some of the mass. So that where the concept of dark matter came. So right now we are at the stage where we are just testing this. We have tested it with observing the sun. We have also tested the design for getting the various parameters, the velocity, the redshift, and still we are working on improving the resolution, so that we can get the actual exact count. And once we get that, then we'll be going on further.
Sorry, Shirang, I have another question.
Yeah.
So, is there any calibration thing in this device? For example, you are measuring the rotational curve of Milky Way, for example.
Mhm.
So, uh, how you can get the idea that rotational curve is correct?
Okay.
So before plotting the rotational curve, we need to know what is the velocity with which we are moving, which is also known as the velocity of standard rest. So
Hmm.
that is one part where we need to calibrate, because everything is moving with respect to another. So we need to first fix the frame of reference with which we are calculating it. So here the frame of reference is between the galaxy and the velocity with which the sun is moving around the galaxy, which is
Hmm.
indirectly the velocity of standard local of rest. So
Okay.
that is already been calculated, which is around 230 kilometer per second. But a recent, just a couple of days back, that also was changed. So with the recent radio telescope observation done in Japan, so it was concluded over there that we are more closer to the center of our galaxy, and we are also moving with a greater speed. But in our calculations, we have considered 230 kilometer per second as the reference. So once we get closer to that, then we can do a rest of the thing. Any more questions on this?
No, thank you. Thank you.
Uh,
So
I
this
have a
is the,
general question.
yeah.
What is the field of view of this telescope, and how do we actually assess it? How we can determine the field of view?
Okay, I think we. I will show the. I will show some pictures and also some calculations that we have done later in the slide. But what we are looking at is a beam width of 22 degrees, sir. So it means that the field of view will be around 22 degrees.
Okay. Okay.
There are certain calculations as well to calculate the beam width or the field of view, as well as you can also try that in simulation while simulating the design of the antenna.
Yeah,
Okay.
it depends
Okay.
upon
Got it.
the size of the antenna, aperture, and the design, the gain, and I'll talk about it in the next few slides if we
Okay.
have time. So,
So you want to carry it forward? Huh?
yeah, I'll take it. Thank you, Sriram. Yeah, once again, yeah, we did the same kind of an assessment as what we did in case of the solar one, which I just explained. We took a series of spectrograms here, trying to assess where we are getting the peak, and then software, and then we analyzed it, and that is how this graph down below is plotted. And this gives some idea about when you detect something, you see those spikes over here, and those spikes are kind of interpreted as the signals which are coming in from the source, and that's how we were able to do the basic detection, and then do a cross analysis of what we have detected is actually right, and so on. Okay, just coming to kind of what components are being used. This is the RTL SDR, which is the SDR, software defined radio. It is made by various companies. We have used something from RTL. There is also something which you can get from Noelec and various other manufacturers as well. So they work from 24 megahertz to 2400 megahertz. That's their bandwidth. And then uh, this talks about the input impedance. It is around 50 ohms and so on. But their analog to digital conversion capacity is around 8 bits. And that is what we have used. Plus, there's also those two filters that we were showing earlier. What we have used for hydrogen line filter is a Saubert filter from Noelec. That's one on the left with the blue color background. And then there's a wideband LNA. This is used as a low noise amplifier, which is to amplify the incoming signal and then feed it to the RTL SDR. That's what we. These are the few devices that we have used from the electronics point of view. Rest of of the antennas, we had to do some modifications to get them right. We explain. Okay, this is the antenna design basics. I will not go too detail into it, but just to give a very brief introduction is that now here's where like the field of view what Professor Saini Saab was asking about the beam width. It tells what is the kind of resolution that it can do when the device is pointed towards a source, and how long can that source be held in its view. So it all depends upon the beam width characteristic, and then and the main lobe where you actually start gaining a lot of data from the source which is emitting the signal. So this beam width becomes very important when you are trying to design an antenna itself. So it depends upon various parameters, right from the aperture of the antenna, and then the orientation, the design that you are following, and what kind of antenna, what type of antenna you are doing, and so on. But there are a few formula which is used for calculating the beam width and trying to resolve it to a particular frequency that you are interested in. And then it will give you what is the beam width. In our case, it was around 1.72 degrees for the parabolic dish that we use for solar radio telescope. It means that it cannot hold the sun for more than 1.2 degrees in the when it moves across in 1.2 degrees, it moves away. That means that the sun signal is lost. It's a very narrow band, narrow beam width in terms of the chromosphere. So you need to keep adjusting the antenna when the sun is moving to keep receiving the signals constantly. So that's something that is what is shown as the net result of when you calculate the beam width and find out how effective your antenna is to receive a signal. So this is something which is very important. And then we did a lot of simulations using software like MATLAB, and then CST, and then there is Whippledy and many other software tools, um, NEC2 and so on, which you can use to simulate your design and find out before actually building the antenna how effective it is in terms of resolving a particular bandwidth, or a particular source, or a signal strength. What would be your gain when you use a particular physical or a geometric pattern to design an antenna. So this is just a snapshot of what we did using MATLAB, and we started calculating the beam width and baseband characteristics for the basic hydrogen line telescope when we built the Mark 1 version. So this has been further improved a lot to narrow the beam width and try to get to a main lobe, which is much more, which has got much more gain and directivity to receive the signal in a continuous way. So these are few parameters that we need to keep in mind when we are designing. This is the whole crux of the whole part of radio telescope design, the antennas. Yeah, these are the few parameters which we need to keep in mind. One is the bandwidth. That means what is that band that you want to operate between, and then radiation pattern and beam width, gain, polarization, and directivity. I'll try to touch upon each one of them very briefly. Um, so bandwidth is where the upper and lower frequency bands that a particular signal is emitted. Say for example, you want to build an antenna which captures all the FM radio signals. So FM radio typically operates between 89 megahertz to around 104 say megahertz. So that's the bandwidth in which this whole thing needs to operate, and that's the fixation of the bandwidth that you want to resolve an FM radio signal and you want to design an antenna for it. I'm just giving an example, and that you keep in mind. And then you start designing something, and then you'll have to find out what is the radiation pattern. Radiation pattern is in which the antenna either transmits or receives the signal, and what is the pattern it follows to resolve. And so it's a function of a main lobe and a back lobe, and there are side lobes. The main lobe is actually the major portion in which all your signal reception or transmission happens, and the gain of this determines the net gain of the system itself. Then you will have to find out the this is the main this the radiation pattern in which the maximum radiation gets either converges or diverges towards the source in which it is transmitting or receiving. So I, I think we don't have to go too much into detail, otherwise it will go into antenna theory, and so we just skip this. And then, of course, we were just talking about the beam width. There are two subdivisions once again: the full power and half power and fractional beam width, which talks about what is the maximum resolution that can happen, and with respect to a particular gain, and yeah, and where is the peak in which your total resolution gets resolved. I will not go too much into all this. So next is the directivity and gain. Directivity is when we are looking at the solar part, where we are saying that whether it is offset or it is a central focus, depending upon the directivity, it means that whether it needs to be directed towards a source or it is offset direction, or the gain talks about the net volume at which the signal is received when it is focused at a particular source. That's few things. And then, yeah, sorry, some question.
Ram, I think we can continue it in next lecture because it is too fast. Because
Yeah,
लगता है कि I
I
think
don't want to
it's
get
too
into.
fast.
I'm just trying to tell that you can build various types of antennas. I just don't want
Okay,
to get
okay,
into
okay.
that. It's saying that you don't have to limit yourself to a particular design for a particular
Right.
application, and you have various types.
Because there are various interesting thing in this talk, so
Yeah.
I don't want that you move it in so fast way.
Sure. Okay. So no, the idea was today to just give a short introduction.
Okay.
I can't put too much into a small hour and a half session.
Right, right, right. So we can also discuss this in our next session.
Yeah. So yeah. Okay. I'll stop presenting. Yeah, that was the idea today. Sorry if I think we have tried to rush up in the last couple of slides. Yeah.
Okay, may I request you to provide a brief introduction about yourself also, so it can be included in the video.
Okay. Um, my name is Ram. I'm a software engineer, uh, and astronomy is one of my hobby, and radio astronomy is something that we wanted to try new, and that's how, as a new avenue which we have been exploring, what we can do as a hobby from the radio parts of the astronomy. And that's how we started a year and a half back to do a couple of projects, and still in the process of building and perfecting those designs that we started for building the reception of sun's chromosphere observation, and then 21 centimeter hydrogen line detection. These were the two home-built radio telescopes that we have been working on, and that's the short introduction.
Thanks,
Sriram, do you
thanks.
want?
Shirang Sapti can also tell about himself.
Uh, Hello, my name is Shrihan, and I am a engineering pass out student from a normal engineering college from Nagpur. That is in 2017, and after that, I have worked at an observatory. So it was a private observatory in Pune, and thereafter I came to Bangalore where I meet Ram, and then we all started with this journey, which Ram right now told you all. So basically, apart from this, I am also looking for my master's study, and I have got two acceptance from Australia right now. So I'll be continuing that once the borders are open. Until now, I'm just doing all this kind of research and trying to improve myself in this field as well as data science field. So that was a short intro about me.
Thank you so much.
Thanks, Ram, for this wonderful talk, and thanks, Srirang.
Thank you for bearing.
Thank you. I think Ram, Srirang, I think it was wonderful because generally we talk about astrophotography, but this is serious knowledge for us. So definitely a bit overwhelming for one session. Definitely we all realize that, but looking forward for the next session. Quite interesting and quite deep as well. I don't think we can grasp all the elements in one go, but it's a great introduction to the field, and we are very proud of having you in our forum, in the astronomy forum. Having known you, I think it's a great honor for us.
They have certainly added a new dimension to astronomy.
Yes, yes, absolutely, absolutely. Thank you, thanks, Paraminder, for organizing this.
Thank you so much for inviting me.
Thank you.
Thanks a
Thank you.
lot.
Okay, thanks to all.
Thank you all. Thank you so much. Good day.
Thank you.